So we've been looking at trig substitution, and the idea is to take advantage of those Pythagorean identities to rewrite our integral into some form where we could find the antiderivative. And we've been looking at some forms. We saw a squared plus x squared. By using tangent, you could take advantage of this identity, right? And if you were using a squared minus x squared, you could take advantage of this identity, the sine squared plus cosine squared equals 1. So the last form we need to look at is what about stuff of the form x squared minus a squared. So remember, the idea is whatever you're going to let x equal, and we always have that a in there. Remember that the a's in there so that when it goes in for x, you have an a squared in both those terms that can factor off. So whatever you put here for the trig function is going to end up squared minus 1 once the a squared is factored out. So when you look through this list for trig function squared minus 1, either of these two, right? If you subtract the 1, you'll have secant squared minus 1 or cosecant squared minus 1. And like we've been saying in all of these, you always have the option to go the cofunction route, but we typically just don't. You'll notice the examples in the text don't. So this is what we really want. If we use a secant, then when you plug that in here for x, you'll end up with secant squared minus 1, which we can replace with tangent squared. So there's the logic of why you would try this in that form. So let's try an example and see how this would pan out. So say we had the integral 2 over square root of x squared minus 9 dx. And recall that there may be other stuff going on in the integral, right? The fact that I see x squared minus a number squared leads me towards this idea. There could be other x's floating around in here, and that's fine. But then that might be a u sub would be a better way to go. So you kind of have to think, well, are there easier routes? And so there's no substitution I can do here. If I do a u sub with x squared minus 9, du is 2x dx, and I don't have an x up top. So I'm out of luck on the easy route. So this makes sense as something to try. So our a in this case is whatever's being squared here. Now, I believe I mentioned before that this doesn't have to be a perfect square. That could be a 7. And then your a is just square root of 7. So we typically use perfect squares just to make life easy for you in your homework. But this could really be any number, x squared minus anything, because a is just the square root of that anything. So x is going to be a secant, so 3 secant theta. And we need to calculate our dx. So remember, derivative of secant, secant tangent. And now we're ready to rewrite our integral. So we've got 2 dx. So 2 times all of that would be 6 secant theta tangent theta d theta, all over square root of x squared, which is 9 secant squared theta, then minus that 9. And again, that's why the a should be 3 there, because now we're going to be able to factor that 9 out completely. Comes outside the square root as a 3, and we'll cancel with that 6. So continuing on, we'll have 2. 9 comes out, becomes 3, cancels with the 6. Secant tangent d theta over square root secant squared minus 1. Which is exactly what I was talking about at the beginning here. We want to end up at secant squared minus 1, so we can use this identity. That is square root of tangent squared. Now, here we run into a slight issue. We've seen this happen in the other two, where we have square root of a square, right? And I mentioned briefly that because of the way the inverse trig functions work, that you didn't have to worry about what was inside here being negative. So in other words, we didn't have to worry about putting an absolute value. It turns out that's not the case in this substitution. So what you're going to notice is when you get a problem like this, notice that x would have to either be bigger than 3 or less than negative 3 for this to be defined, right? This is defined for x greater than 3 or x less than negative 3 because of we can't have negatives under the square root. But in order to argue that I don't need an absolute value here, to make life easy for us, you'll notice in these problems there will be a domain restriction. Without this domain restriction, then at this stage we would have to put an absolute value, which means we'd have to break it into two cases, when tangent is positive and when tangent's negative. When you put this domain restriction, which the book will already have in there for you as part of the statement of the problem, that will guarantee that this can't be negative. Why is that? Well, you have to go back to this. What is the connection between x and theta? Well, what is theta? Theta involves secant inverse, right? And if you look at secant inverse, making x greater than 3 will make this tangent positive. If you look in the text, there's a nice diagram in there showing you that. But this is kind of a cheat, too. So if you see a domain restriction in a problem, that would lead me to think that we're doing this substitution, because I know that this substitution, just to be nice to the student, requires that domain restriction. So when I simplify this, I don't have to worry about the absolute value. So it's secant theta, tangent theta, over just tangent theta. No absolute value needed, and because of that domain restriction. Now this simplifies down to just secant and as we saw before, the antiderivative of secant is that kind of awkward one that you should probably just memorize because the derivation is tricky. So the antiderivative of secant is natural log absolute value of secant plus tangent. And then lastly, we want to get back to x. So recall, we could make a little diagram over here. What does this tell us? If we look at this, secant is, from that we have that secant theta is x over 3, right? So I'm going to draw a right triangle where that is the case, where secant theta is x over 3. So what is secant? Secant is 1 over cosine. So really I want to draw an angle where cosine is 3 over x. Cosine is adjacent over hypotenuse. Right? So what I've drawn is a right triangle where secant of theta is x over 3, hypotenuse over adjacent. Then I just solve for the third side, which we can always do by Pythagoras. And I've pointed out on each of these examples that it should come out looking like this. It's a good check on your work that missing side should be that expression, which it is. And now we can say what these functions are in terms of x. Secant, well, that's the easy one. Secant is just x over 3. But tangent is opposite over adjacent. So we end with that. And as we've seen in these before, the textbook is very fond of using a bunch of logarithm rules to simplify this. I'm fine with you just leaving it in that form. You know, you could combine this into one fraction, and then you've got a rule about logs of quotients. And just be careful, because one of those logs is a constant, and it just sort of absorbs into the constant of integration. So I'm fine with you just leaving it like that. So x squared minus a squared leads us towards trying this a secant. That doesn't really have to be a perfect square, but there does need to be a domain restriction, which you will see in the problem, which that domain restriction leads to us being able to avoid right here. We went from that to that. We avoided absolute values. That's just sort of a nice addition for us. And so those are our three situations, either with tangent, sine, or secant. But you could use cotangent, cosine, or cosecant. Works out the same. It's just kind of traditionally we use the non-co function.